Today we're going to integrate the absolute value of x. Now you might think, okay, well typically we integrate some absolute value of some function and it's a definite integral with bounds, but this is kind of special because we're able to actually integrate this with integration by parts. Typically when you're dealing with absolute value integrals, you can't do that because you're going to need some sort of du if you're trying to do u substitution, and it just doesn't work. So with this is a really special case because you really often can't do this. So let's see how we start. So like I said, we're going to use integration by parts, assuming that we already know the derivative of the absolute value of x. So I'll get to that in a second. So let's just start. So let's see here, we need a u and a du, and we need a dv, and we need a v. Okay, so our u is going to be absolute value of x, and I'm putting this here because we don't know how to integrate it, so we can't put it as our dv. For our dv, we're just going to have dx, or just 1 basically. And we can easily integrate that and get x, so v is equal to x. But our du, remember that the derivative of the absolute value of x, we have two ways of expressing that. We can express that as x over the absolute value of x dx, or absolute value of x over x dx. These two functions are the exact same, so we're free to choose whichever is most convenient for us. So we'll get to that in a second because it will be a very important choice. So we have our setup. So now let's just do the integration by parts. So the first part is uv. So we have x times the absolute value of x minus the integral of v du. So we have x times our du. So which one would make sense? Well, I think this one makes the most sense because we have this x on the bottom that can cancel out with this x up here. So we have times the absolute value of x over x dx, and so like I said, we're going to cancel out this x with that x, and we just have the absolute value of x left over. So let me write this first. So we have let me do it over here. So we have the integral of the absolute value of x dx. This is equal to x times the absolute value of x minus the integral of the absolute value of x dx. Now you might think, okay, well, we just need to evaluate this, but wait, we don't know how to do that. But in fact, that's our original problem. And we have this equation here. This integral is equal to this expression minus the same integral. So if we just added this integral to both sides of the equation, so let me get this red marker here. If we added the integral of absolute value of x dx to both sides, then what we would basically get, we can basically just do this, and what we have now is 2 times the integral of the absolute value of x dx, and this is still equal to x times the absolute value of x. Isn't that crazy? So we have, hold on, let me make that a little better. We have 2 times this integral is equal to that. So if we just divide by 2, we're done. And that's it. Now, do we need a plus c? So yeah, the integral of the absolute value of x dx is equal to x times the absolute value of x over 2 plus c. So this is a really cool way of doing this, and it's very, it's not a very common way to solve an integral to have some sort of equation like this, but it's really cool whenever you get to use it. One last thing, I want to make sure that this actually makes sense. So let's just do this. So if we have some function here, absolute value of x, so let's say we're trying to find the area from, I don't know, from here to here, right? And so we would have to do the whole, actually let me make it more interesting. So we would do it from here to here, so from here to here, so all this area in between. So we would, if we wanted to, we would say like the integral from, I don't know, a to b, so the integral of a to b of absolute value of x dx, it would just be 1/2, I can factor out the half, times x times the absolute value of x from a to b, basically. And so we could do it this way. And this isn't very much different from just the integral of x, because if we have the integral of x dx, that's equal to x squared over 2 plus c. And you would basically do the same thing. The only difference is that we can write this as x times x over 2 plus c. And now you can see that this is very similar because we have x times x over 2 plus c. Here, the only difference is we have absolute value bars around the second x. So you can see the similarities between these. And the reason why this one has an absolute value of x is because we have to account for this portion that goes up, and it's like the positive version of that. So that's basically why. So this should make sense. For positive values of x, these two equations are going to be identical for positive values of x. But for negative ones, the only difference is that this guy is going to make it actually positive. Yeah, because basically if you plug in a negative value for x, this is going to be negative, this is going to be positive because the absolute value of a negative number is positive. So this expression, it will be negative, but remember whenever you're using the fundamental theorem of calculus, it's going to be this minus this, and if this is negative, then it's basically just adding on. So you're adding on more area in the end. So that's kind of the explanation of what's going on. So I hope that last part made sense to you. And if not, let me know in the questions. I can explain it in a different way. So yeah, I hope you guys enjoyed this video. Thank you so much for watching, and I'll see you in the next video. Bye guys.